Good morning, everyone, and a warm welcome to all of you. I am delighted to have the opportunity to speak with you today. Today's presentation is titled System Suitability in Gas Chromatography, and it's an important topic for anyone working with GC techniques. We will explore what system suitability means, why it's crucial, and how to ensure your GC system is performing optimally. So let's get started and dive into the fascinating world of gas chromatography. System suitability tests, or SSTs, are a crucial part of ensuring that our gas chromatography system is ready to deliver reliable and reproducible results. These tests are performed either before starting the sample analysis or during the process to verify that the system is functioning properly. When we talk about SSTs, we're really focusing on performance parameters like resolution, which tells us how well our peaks are separated, precision, meaning consistency in our results, sensitivity, or the system's ability to detect low concentrations, and column efficiency, which relates to how effectively the column separates compounds. According to the United States Pharmacopoeia, these tests are essential for confirming that our GC system is performing optimally. This is especially important because it helps us trust the data we generate, whether we're analyzing pharmaceuticals or other complex mixtures. In the context of our overall presentation, it's important to remember that SSTs are not just a regulatory requirement, they're a quality assurance tool. They ensure that our system is capable of producing accurate and reproducible results, which is fundamental to the integrity of our analytical work. This is why organizations like USB, ICH, and other regulatory bodies make SSTs mandatory. They help maintain high standards across the board. Now, let's talk about the purpose of system suitability. First, it's essential to confirm that the GC system is functioning properly. This means checking that all components are operating as they should, so we can trust the data we're generating. Next, we need to ensure that the chromatographic performance meets the method requirements. This involves verifying that our separation, resolution, and sensitivity are within acceptable limits, which is critical for reliable results. We also have to be vigilant in detecting any issues early on, such as column degradation, leaks, or detector instability. These problems can compromise our analysis, so catching them beforehand is key. Lastly, maintaining compliance with regulatory expectations, like those from USB, ICH, and FDA, is fundamental. It ensures our methods are not only scientifically sound, but also compliant with industry standards. All these steps together form the core purpose of system suitability testing, making sure our GC system is ready and capable of delivering accurate, consistent, and compliant results every time we run a sample. Let's talk about retention time, or TR, which is essentially the amount of time it takes for an analyte to pass through the system from injection to detection. This is a crucial parameter because it helps us identify compounds based on how long they stay in the system. For example, if peak 1 appears at 4.5 minutes and peak 2 at 5.3 minutes, we can distinguish between those two analytes easily. Retention time is also key for ensuring reproducibility, meaning if we run the same sample multiple times, those peaks should appear at the same times each run. Moving on, other important system suitability parameters include resolution, or RS, which tells us how well two peaks are separated. The theoretical plates, or N, give us an idea of the column's efficiency. Higher N means better separation. The tailing factor, T, indicates whether peaks are symmetrical or skewed, affecting our ability to accurately quantify analytes. Repeatability, expressed as %RSD, measures how consistent our results are across multiple runs. And the signal-to-noise ratio, SN, helps us determine the quality of the signal. Higher SN means clearer, more reliable detection. All of these parameters, retention time, resolution, theoretical plates, tailing factor, repeatability, and signal-to-noise ratio, are essential for assessing system suitability in gas chromatography. They ensure our analysis is accurate, reproducible, and reliable, which ties back to the overall goal of achieving high-quality analytical results. Let's continue with slide 5, where we focus on some additional key parameters that determine system suitability in gas chromatography. These parameters are essential because they influence the reliability and accuracy of our analysis. First, we look at the column efficiency, which is often expressed as theoretical plates. This tells us how well the column separates components. Higher efficiency generally means better separation. Next, we consider resolution, which measures how well two peaks are separated from each other. Good resolution means we can distinguish closely eluting compounds clearly. Column selectivity is also critical. It refers to the column's ability to differentiate between different types of compounds based on their chemical properties. Then we have the injection volume and mode, which can impact the peak shape and sensitivity. Proper injection technique ensures reproducible results. Finally, the overall system robustness is vital. It's about how well the system performs over time and under varying conditions. A robust system minimizes fluctuations and maintains accuracy. All these parameters interconnect to ensure our GC system is suitable for the analysis at hand, providing consistent, reliable, and precise results that align with our analytical goals. Let's continue by exploring the key system suitability parameters in gas chromatography, or GC, as we see here. These parameters are essential because they help us determine whether our GC system is performing optimally before we start analyzing samples. First, we have the retention time, which is the time a compound takes to pass through the system. Consistency in retention times indicates that our system is stable and reliable. Small variations might suggest issues like column degradation or slight fluctuations in temperature. Next, the peak shape and symmetry are crucial. Ideally, peaks should be sharp and symmetrical, as this reflects good separation and efficient column performance. Asymmetrical peaks could point to problems like column overload or carrier gas flow inconsistencies. Then there's resolution, which tells us how well two compounds are separated. High resolution means clearer differentiation, which is vital for accurate identification and quantification. If resolution drops, it could lead to overlapping peaks and unreliable results. Finally, we consider system pressure and flow rates. Maintaining consistent pressure and flow ensures reproducibility. Variations here can affect retention times and peak shapes, so regular checks are necessary. All of these parameters connect back to our overall goal, ensuring accurate, precise, and reproducible analyses. Monitoring and controlling these parameters helps us trust our data and maintain high-quality results in our GC analyses. Let's continue our discussion on key system suitability parameters in gas chromatography. As we saw earlier, these parameters are essential for ensuring our GC system performs reliably and produces accurate, reproducible results. On this slide, we're focusing on some additional important factors. First, we have the concept of system precision, which refers to the consistency of repeated injections under the same conditions. It's crucial because it tells us how dependable our system is over time. Next, we look at baseline noise. This is the small fluctuations in the detector signal when there's no analyte present. A low noise level is vital for detecting low-concentration analytes accurately. Then, we have the signal-to-noise ratio, or SN, which helps us determine whether a peak is distinguishable from the noise. A higher SN ratio indicates a more reliable detection. Lastly, the aspect of peak symmetry or tailing is important because symmetric peaks are easier to integrate and quantify accurately. Tailing peaks can complicate analysis and reduce confidence in our results. All these parameters connect back to our overall goal, achieving precise, accurate, and reproducible chromatographic data. By carefully monitoring and controlling these factors, we ensure our GC system remains suitable for the analytical work at hand. Let's continue exploring the key system suitability parameters in gas chromatography. As we discussed earlier, these parameters are essential for ensuring our GC method is reliable and repeatable. On this slide, we're focusing on some additional important factors. First, sensitivity is a critical aspect. How well our system can detect small amounts of analyte. A highly sensitive system allows us to identify even trace levels, which is often vital in complex analyses. Next, we have resolution, which refers to the ability to distinguish between two closely eluting compounds. Good resolution ensures our peaks are well separated, making quantification more accurate. Then, we look at repeatability or reproducibility. This involves running the same sample multiple times to see if our results are consistent. It's a key indicator of the method's precision. Finally, the stability of the system over time is also crucial. We need to verify that the system maintains performance during continuous operation or over extended periods. All these parameters, sensitivity, resolution, repeatability, and stability, are interconnected. They collectively ensure that our GC system produces reliable, accurate, and reproducible results, which is fundamental for making sound analytical decisions. Remember, regularly evaluating these parameters helps us maintain confidence in our analyses and troubleshoot any issues that may arise. Now, let's walk through the general sequence for a standard USB practice when it comes to injection ordering. First, we start with a blank or diluent injection. This helps us establish a baseline and ensure the system is clean before we begin. Next, we run the system suitability standard, which we typically do in 5 to 6 replicates. This step is crucial because it confirms that the system is performing properly and consistently before analyzing our samples. After that, if applicable, we run a calibration standard. This step is important for establishing the relationship between concentration and response, ensuring our quantitation is accurate. Then, we proceed with the sample injections themselves. These are the actual samples we're testing, and we inject them in a sequence to obtain our data. To maintain accuracy and account for any variability during the run, we insert a bracketing standard after every 5 to 10 samples. This helps us verify that the system remains stable throughout the entire batch. Finally, at the end of the sequence, we run a final standard or blank. This last step confirms that the system has remained clean and stable throughout the analysis. So that's the typical injection sequence. It's designed to ensure reliable, reproducible results while monitoring system performance throughout the process. All right, let's take a closer look at this complete SSD example. Here, we've got some specific data points to consider. The first are the retention times, TR1 at 4.5 minutes and TR2 at 5.3 minutes. These are important because they tell us how long it takes for each compound to pass through the system. Next, the peak widths at baseline, W1 and W2, are 0.25 and 0.3 respectively. Narrower peaks generally indicate better resolution and sharper separation. Speaking of resolution, in this example, we have a resolution of 2.91, which is well above the minimum pass criterion of 1.5. That means the peaks are sufficiently separated. The percent RSD, or relative standard deviation, is 0.97%, which is comfortably within the acceptable limit of 2%. This indicates good precision and repeatability of the method. The plate count here is approximately 4,992, which reflects the column's efficiency. Now let's connect this to the USB acceptance criteria. Resolution needs to be at least 1.5, and as we saw, ours is 2.91, so that's a pass. The tailing factor, which we don't have explicitly here, should be less than or equal to 2 for good peak shape. The percent RSD should be less than or equal to 2%, and since ours is only 0.97%, that's another pass. Lastly, the plate count should meet the method-specific requirements, which it does here with nearly 5,000 plates. The signal-to-noise ratio should be at least 10, and although we don't have that number explicitly, these other parameters indicate a robust, reliable method. Overall, this example showcases how all these parameters come together to ensure method quality and compliance. Let's walk through a practical example of a complete SSD evaluation. This slide highlights how we can apply the concepts we've discussed so far in a real-world scenario. When we perform a full SSD evaluation, We're essentially analyzing each step carefully, from identifying the system's goals, assessing potential threats, to evaluating safeguards. This process helps us see the bigger picture, ensuring all aspects are considered and that our system is as secure as possible. Remember, the goal of this exercise is to not only identify vulnerabilities, but also to develop effective strategies to mitigate risks. By going through a complete evaluation like this, we reinforce the importance of a thorough, methodical approach, one that ties back to our overall theme of building resilient and secure systems. So, this example serves as a practical demonstration of how the principles we've discussed come alive in real-world applications. Let's take a look at some common problems you might encounter in your chromatography processes. One issue is low resolution, which often results in column degradation over time. When the resolution drops, it becomes harder to distinguish between compounds, which can affect your results. Another problem is high tailing, which usually indicates contamination or possibly some issues with the column itself. This tailing can distort your peaks and make interpretation more difficult. Then we have low plate counts, which are a sign that the column might be damaged or not functioning optimally. This impacts the efficiency of separation. High % RSD, or relative standard deviation, points to injection errors, maybe inconsistent sample volumes or other injection issues. Now, to avoid these problems, there are some best practices I want to highlight. First, always use fresh standards to ensure your calibration is accurate. Properly conditioning your column before use helps maintain its longevity and performance. Maintaining the purity of your gases is also crucial, because contaminated gases can lead to issues like tailing or contamination. And finally, regular calibration is essential. By doing this, you ensure your system stays accurate and reliable over time. Connecting all these points, following these best practices can really help you prevent common problems and keep your chromatography running smoothly, ensuring high-quality, reproducible results every time. In conclusion, SSD plays a crucial role in ensuring the reliability of GC analysis. It's not just about quality assurance, it's also critical for regulatory compliance, helping us meet industry standards and avoid potential issues. Before we even analyze samples, SSD helps confirm that the system is fully ready and performing optimally. This step is vital to prevent errors and ensure consistent, valid results. System suitability in GC is a key quality control measure that we rely on heavily. By evaluating parameters like resolution, efficiency, symmetry, and precision, we can confidently verify that the system meets USP requirements. Ultimately, this process helps us produce reliable data, maintain high standards, and uphold the integrity of our analytical results. For further support, please feel free to contact us. We're here to help you with any questions or additional information you might need. Thank you so much for your time and attention today. We appreciate your interest and engagement, and we look forward to supporting you moving forward.